Okay, so this week we'll be talking about counting with principles. Okay, you can't see me. That's all right. All right, can you guys see my screen now? Yes. Okay, great. Okay. So this week we are talking about counting principles. I'm going to start off talking about countings with charts. So see if you can answer the first question. If two dice are rolled, how many possible outcomes are there? Right. The answer is actually 36. Nice job to those who got it. I'm not sure how you got 18, but I'll explain it. Okay, so like this is counting using charts. So sometimes math counts uses problems with dice, and those always confused me. So an easy way to like think of the problem is to draw a chart. That was always like what I would do. It's like a little bit slower, but it's always like gonna be correct. So for example, if I draw the actually showing the chart is probably easier. So if you look at this chart right here, so this top half is dice 1, and then the bottom left is dice 2, and then you see all the possible outcomes. For example, 1 1, 1 2, 2 1 3, continuing, and then so it's like drawing this chart will take a little bit of time, but like it's good because you know that you're gonna get the problem right per se. And then so 36 outcomes. You can also think of it like if dice 1 there's 6 possible ways and dice 2 also has 6, then 6 times 6 equals 36. So that works. Okay, so if you want, you can use this chart, or if you think it's quicker, you can use your own way, but I always like to use the chart. So example number 2, two dice are rolled. How many ways are there to roll a sum of 5? So like here's a chart over here. You can try to use that if you want. So see if you guys can get this problem. Right, so the correct answer is 4. Nice job, guys. But as you can see, I drew a little chart over here, and that didn't take much time. It took a little bit of time, but like still, it's not much more than you would have used. But like so, through my chart over here, I can count the sums of the ones that sum up to 5. So this sums to 5, this sums to 5, this one, and this one. So there are total of 4 that sum to 5. Right. So how about what if I ask the question, how many sum to, let's say, 8? So how many dices can you roll so that the sum is 8? And you guys can draw out the chart if you want, or you can just think about it. Okay, nice. The answer is 5. So like, if you did draw out the chart, you could see like 1, 2, 3, 4, 5 eights, so a total of 5. So drawing out the chart really helps, and it doesn't take very long. Okay, so try it yourself. Um, a cube has faces numbered 1, 2, 3, 4, 5, and 6, and another cube has faces number 2, 4, 6, 8, 10, and 12. If the cubes are rolled, how many ways can you roll it so that the sum is 8? Okay, so I'll start the chart over here. You guys can draw the chart if you want. Okay, right. The correct answer is 3. Nice job, guys. So like, I drew a chart over here. So if you can see, there's an 8 here, there's an 8 here, there's an 8 here. So even like right here, I wouldn't even have to continue all this because everything after this is going to be greater than 8 anyway. So we just have 1, 2, 3 8s. Okay, so try this problem. 2 dice are rolled and their faces multiplied. How many ways are there such that the product is a prime or ends in 6? You can also draw a chart if you have products as well. So you just, instead of summing it, you product it, which I'll do over here while you guys try the problem. So like, since this problem is a little bit more complicated, it's probably better if you draw a chart and then count number of ways the product is a prime or ends in 6 out of these 36. Sorry, I wasn't talking then. Okay, so the answer is 12. So if you count from the chart, so it's like better to list out the chart. It might take a little bit of time, but you'll know you get the answer for sure. So if you count it out, I've gone ahead and circled the numbers that are prime or end in 6. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you get your total of 12 ways. So the product is prime radians in 6. And here's it drawn out here without the other numbers included. So like for simple problems that you can think logically, it's probably better if you don't use a chart, but for more complicated problems and you don't want any mistakes, it's probably better if you use a chart. So the second one, other than using a chart, is counting using tree diagrams. So tree diagrams are helpful sometimes when you don't have too many numbers. So for example, how many possible outcomes are there if you toss a penny and a nickel at the same time? As in like heads, tails, heads, tails. So see if you guys can get this problem. Right, nice job. So the answer is 4. Like you started here, and then first off, you can either have a head or a tail, and then for the next chart, you can have another head, and then you can have your original heads, and then another tail.
User, and a factor trade user.
Okay, sorry about that. So, and then from this part, you already have your tails originally, and then you can now have the heads, or you have your tails originally, you can have the tails. So you have 4 different ways. Nice job. So you can also think about it logically, just like 2 times 2 is 4. So heads, 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 tails, tails, heads, or tails, tails. Okay. Okay. So a designer has 3 fabric colors. So just read this problem and see if you can solve it.
Speak. I can't speak. What?
Right, so the correct answer is 12. So for this one, you could use a chart, but we know that it's easier to just, if you think about it, using counting, just 3 for the first one, so 3, 4 for the second one, times 4, so 3 times 4, you get 12. You can also draw a chart, which is shown right here. And then 3 times 4 equals 12. So this is one where probably using a chart wouldn't be a good idea, but like you could. However, in this case, so how many 4-digit numbers can be formed using the digits 2, 3, 4, and 5? Okay, so right, the correct answer is 24. There's kind of 2 ways to approach this problem. First way would be using the counting principle. For example, for the first digit, we have 4 ways to place it. For the second digit, we have 3 ways, because you can't use this digit anymore. And the next one, we have 2 ways equals 24. Right? So you can think of it that way. You can also think of it, so let's say the first digit is 2, then the next digit can be 3, 4, or 5. The next digit after that can be 4, 5, for 3, since you can't repeat, and if it's 4 it has to be 5, and if it's 5 it has to be 4. And you can count it out this way. There's 6, so there's 6 if 2 is the first digit, and you can either have 2, 3, 4, or 5 as the first digit, so 6 times 4 equals 24. So I guess that's like a good way to show it, but I don't know if you would use charts in this way either. Okay, anyway. So counting using water pipes. I think this is like my favorite thing ever in math. Counting is, it's kind of like fun, but it's also a good way uh, to like think about a math problem. So like, for example, there's a water pipe. So in this problem, it's called counting using water pipes because we're imagining water is flowing through pipes. So for example, let's say I have a square right here, and then the question is, how many different ways can I get from point A to point B such that I'm either moving to the right or down? So how many ways can I get from point A to B such that I'm moving from the right and down? Right, so the answer is obviously 2, right? So there's one way here, one way, so there's one way here, and then one way here. So then that's 2 ways. But if the problem gets a little bit more complicated, so for example, how many ways can I get from point A to point B using the same rule? I'm only either moving to the right or down. So how many ways from point A to point B? So for example, one path I could use, let's see if I can draw it in a different color. Red. So one path I could take would be this path. And another path could be this path, and then this path, etc. Right, so the correct answer is 4. Oh, this is 6, sorry. So again, if I draw it, so counting, like right now, it's still not too hard. It's a little bit harder than originally, but it's still not too hard from point A to point B. We can count one path here, another path here, another path here. So there's 3 paths. Another path here, 1, 2, and then 3 paths. And you can count out 3 plus 3, 6. So how about, let's draw another little square here. And then instead of that, let's draw a 3 by 3. Now, how many ways are there to get from point A to point B? So when you're trying to think of this, it gets a lot harder because there are a lot more different ways you can get from point A to point B. So this is where counting using water pipes comes in handy. So it's a lot of fun. It's kind of like a game. So if you see like right here, typical addition rules. So counting using water pipes, what that means is you're kind of imagining water flowing through pipes. So for example, water originates at point A. So at point A, hang on. So let me see if I can get this bigger. So this is our original one, right? From point A to point B. And then we said that there are 2 ways. So we originate from A. So A, we're always having a start at 1. So 1, right? So we always begin at point A with 1. And then this continues flowing. So since it's a corner, nothing really changes here. So it continues being 1. This is a corner. It continues being 1. So then at the end, we get 1 plus 1. So there's a total of 2 ways to flow from point A to point B. So our next one that we just talked about was if we have a square like this, and then we have a little cross here, and then we already know there's 6 ways because we counted out 6 ways. So let's try using water pipes to do this. So it starts out at 1, and then whenever it comes to this little like branching part, it branches out each as 1. Like that. And then this top is going to branch out each as 1 as well. And then when 2 points meet, they add together. So like this example right here, when you have 2 points meeting, they become 2, and then 2 branches out 20. I'm not sure if that's right. I haven't checked that yet, but we'll come back to that. So when 2 points meet at 1, they branch out to be 2. So this branches out to 2, and then this branches out to 2. And then since this one up here is continuing and hits a corner, nothing happens, 1 right here. This one hits a corner, nothing happens, 1 right here. And then now right here, 1 and 2 meet. When 1 and 2 meet, you add them together when points meet. And this comes out to be 3. And then 1 and 2 meet to be 3. So the number of ways to get from A to B is 3 plus 3, which equals our answer at 6. So this was the exact problem I just talked about. So it's like the answer is think about water flowing in pipes, and the starting point is the source of the water. When 2 or more branches of water meet, they add, and the addition carries on to the next segment. So right here, 1 continues since it's not meeting. At this point, it meets, it becomes 2, and then 2's continue. 1 is right here, 1 and 2 meet, they become 3, and then 3 meets, and then becomes that. Okay, so let's try this problem. Example number 2 says, in this plane figure, only downward movement is allowed. Find the number of paths from A to B. So it's just asking how many ways can you move from A to B. So try using the water thing and then see what you get from that. Oops, sorry. Okay, and I'll do my best to draw this figure over here and then start the water pipes. Right, so the correct answer is 11. Nice job, guys. I don't know if you're using water pipes, but some problems get harder and you can't really count them out, but nice job if you did. So I'll start like the water pipes. So initially it's 1 branching out from everywhere. And at this corner, nothing happens. So then 1 continues here, 1 continues here. At this corner, nothing happens. So 1 continues here. So then at this point right here, these 3 ones meet together and you add these ones and they become 3. So then 3 leaves in each of these. And then at this point right here, 1 and 3 meet, so they become 4. This 3 is continuing all the way to B. And then 1 and 3 meet over here, so they become 4. So then it's 4 plus 4 plus 3, which equals 11. So that's an easy way to think about it. So let's try a little bit of a harder one. So this one, I think probably you're going to have to use water pipes or else you can't solve it. It just takes too long and there's too many like ways you could count wrong. So how many paths from A to B if you can only walk from left to right and from down to up? I think it's actually from up to down, or down to up. Oh, wait, it is from down to up. Okay, so I'll let you guys solve this. Everybody's saying 32, I see. Oh, okay. I'll work through the water pipes and then we'll see where you guys went wrong. Hopefully you guys tried using water pipes. It's a really fun method. At least I think so. Okay. So I'll do it in red so you guys can see it a little bit better. Okay. So we start off at A. So A branches off as 1. You don't have to use the arrows if you don't want. And then, so nothing happens here, so 1. Nothing happens here, so 1 continues. And then these two meet, so they add to become 2. So 2's come out. And then nothing happens right here, so then the 1's continue. Nothing happens here, so 1's continue. Nothing happens here, so the 1 continues right here. Okay, and then at this point right here, the 2's add together, so the 2 and the 1 add. The 2 and the 1 add to become 3. And then at this point, also the 2 and the 1 add to become 3. Okay, sorry. I was just making sure I was doing it right. Okay, so then at this point, the 2 and the 1 add right here. So the 2 and the 1 add to become the 3. The 3's leave here. So then right here, the 1 continues. So then the 3 and the 1 right here add to become 4. At this middle point right here, the 2 adds to the 3 and the 3. So that becomes 8. So 8 comes out here. At this point right here, the 1 and the 1 and the 3 add, because there's a 1 here, and a 3. That becomes 5. Hang on, this should also be 5, sorry. So it's like easy to make mistakes, but it's easy to also like catch yourself because it should be like parallel. Okay, so 1 and the 1 and the 3 add here, so that becomes 5. 8 and the 5 add right here, so that becomes 13. 8 and the 5 also add here, so that becomes 13. So your final answer should be 13 plus 13 plus 8, which actually equals 34, right? So as you can see, like, it's easy to make mistakes, but it's easy to catch your mistakes. And also, if you do it in a timely manner, it shouldn't take too long. And you just have to take it like slow, make sure all your water pipes are the same, right? So the answer is 34. Okay, so I think those are really fun, so let's do another one. So like right here, you can see, start off 1, come to an intersection, nothing happens, 1 continues. If you come to an intersection and you have another number, you add those numbers together. And you go from there. Okay, anyway, so let's try number 4. This one you're also forced to be used water pipes, or else it's too easy to make like a careless mistake and like just like it's too easy to not count 1 and just like overlook something. So this one is going to be a little hard to draw, but I'll try to draw it to the side. And I'll enlarge the picture for you guys. Okay, so I kind of drew it to the side, and the problem asked from point S to point T. So if you kind of like start the water pipes down near S, and then try and go from there and try to make no mistakes, you should get the correct answer in the end. And you should always be moving from left towards the right, or down to up. So this one's a little bit more complicated, so I'll let you guys sit on it for a while. Right, so the correct answer is 14. Nice job. I hope everybody tried to use the water thing. Um, so since most of you guys got it, I won't like go through each step, but I'll just show you how you do it. Um, the water starts here at 1, and it branches off at 1, starts here at 1, branches off 1. This point, nothing happens, so it continues as 1. This point, these two ones meet, so they come out as 2. 2, and this point right here comes out with 3. 3 moves on. So it's just like you continue, and the little steps come together into the end where you have a 9 and a 5, which is 14 in the end. Okay. Okay. I'll actually, oh darn. I don't know if you guys saw the answer. I hope you didn't, and if you did, I hope you still did. Anyway, so this one is actually from MathCounts, so it's very applicable. And what's nice is they've already given you the arrows. So it's like, using only the path, how many different routes are there from A to J? So even if you just saw the answer, still try to do it. So again, just think of it like water pipes, and they've already drawn out the arrows, so it should be a little bit easier. So it starts at 1, and if it doesn't meet anything, it continues as 1. So for example, this one continues as 1. And then these two meet right here, so they go off as 2. So
Come on.
Okay, the correct answer is actually 22. Nice job to this person who got it. But I'll walk through it real quick. So ones start here, and then if you follow the arrows, you can see what they should branch off to. So like here, there's nothing that's going to happen here, so the ones are going to continue with the arrows. Sorry about that. Right, so at this point right here, the 2, 1, and 1 converge. So, right, I see some people are getting the 2, 1, and 1 converge, so they should come out as 4, as so. And then the 4 and the 1 and the 1 here meet up, so they become 6. And then the 4, actually, yeah, so then this arrow right here comes here. So I can't add these up together because there's still an arrow here, number I haven't added. So then the 2 and the 4 become 6s. So at this point I can add them up since like you see this arrow is finally there at these 3 arrows. So the 6, 4, and the 6 become 16. And then 16 plus 16 equals 22. So just since they have already drawn out the arrows, you just follow the arrows. Start off at 1 and then continue. Okay. Let's do one more thing, and I think we're going to end it since I'm not feeling too well. Okay. So next principle after the water pipes is called the sum rule. I think this is more of like a logical rule. It's like if an event E1 can happen in one ways and E2 can happen in two ways, and EK can happen in NK ways, if any event this happens, the job is done, then the total number of ways to do the job is this. So it's just saying if one specific thing has X number of ways and another specific thing has Y number of ways, and you want it to find, and if they both do the same thing and they're both counted, then you just add the number of ways you can get them. So I mean, it's kind of more logical, so we're just going to go with examples. So how many ways can one book be selected from a bookshelf of 5 paperback books and 3 hardcover books? So I think the example helps explain it a little bit. I think you guys might be overthinking this problem a little bit. It's just how many ways can one book be selected from 5 paperback books and 3 hardcover books? Right, the answer is 8. Yeah. So it's like the event is to select one book, and it doesn't matter if it's hard or paperback. So it's just from 5 books, you can select 5 ways to select one book, and from 3 books, there's 3 ways to select one book. Okay. So a palindrome is a number that is written the same forward and backwards. How many palindrome numbers are less than 1,000 are there? So instead of just letting you guys do this problem, I'll explain it because that'd be a little bit easier. Okay, so using this method, we split our total number of numbers into little sets. So it says it's easier to count the number of palindromes less than 1,000 if you split them into different kind of sets. So for example, the first little set we're going to split up is 1 digit. So in the 1 digit palindromes, there are 1, 2, 3, 4, all the way to 9. So all these numbers are palindromes, so there are a total of 9 here, because it's the same written forward and backwards because it's just 1 digit. So next set we're going to use is the number of two-digit palindromes. So basically, we're breaking 1,000 into different little things. So if we kind of write out the two-digit palindromes, it's just basically 11. So it's just digits that look the same: 22, 33, 44, 55, etc. onto 99. So there are also a total of 9 two-digit palindromes. And then the last one we have is three-digit palindromes. And I think these are like, they seem to be a little bit harder to sort out. But there's like an easy way to kind of list them out. So for example, let's say 101 is the first one, and then the next one would be 111. So the middle digit doesn't really matter after you have the two side digits, so 121, 131, etc. So there'll be 9 of these, so total 9. And then, sorry, no, my mistake. There'll be a total of 10 of these. So onwards until you get to 191, and then there's a total of 10 of these. And then if you list the next one, 2 with 2 as the first digit, so 202 is the first one, 212, 222, and etc. until you get to 292. You'll have a total of 10 of these as well. So then your first digit could be 1, 2, 3, 4, 5, 6, all the way to 9. So you have a 9, and then each one has 10. So you have a total of 90. So that might be a little harder to think of, but so 90 here, 9 here, and then 9 here. So then we can answer the question, how many total number of palindromes are there? With 108. But actually, I made kind of a mistake. Or not really a mistake. It's kind of different from the solution. Okay. Solution has 109. It's kind of like how the question is worded if 0 is really counted. So you can count 0 or you cannot count 0. I think this is a problem we made. Okay. So 0, I guess 0 works. So if you have 0, then just one more here, 0. And then you have a total of 10. So 109. Okay. Anyway, so that problem was just to like show you an idea. So let's try this problem. Park Middle School Math Club consists of 6 boys and 4 girls from the 6th grade, 4 boys and 3 girls from the 7th grade, and 5 boys and 5 girls from the 8th grade. How many ways are there to select one student from the club to represent the school for a big math competition? Actually, this problem is kind of easy, yeah. It doesn't make very much sense. So just, I'll just go ahead. Nice job to this person. I'll just go ahead and say it's just the sum of everything. Right. Okay. So it's just 27. Okay, so now on to the one of the more important rules. So this is probably the most important rule in math. Okay. So this is called the product rule. So if a task consists of k separate parts, the first part can be done in one way, the second part can be done in 2 ways, and then so on. Then the total number of possible results is the total in 1 times in 2 times in 3. So the total number of ways for each specific thing. So this, I think most of you will already know this, but it's like saying if you have 4 different kinds of soups and then 2 different kinds of drinks, and then how many ways are there to have 1 drink and 1 soup? It's just 4 times 2. And then one little note, if you take something like, let's say 5 times 4 times 3 times 2 times 1, this can be also written as 5 to the factorial. So basically anything x, so like n to the factorial, is equal to n times n minus 1 times n minus 2, all the way, etc., until you have n until you have 1. So right, so like right here, someone said 4 to the factorial is equal to 24. So how you get that is you write out 4 times 4 minus 1, which is 3, times 4 minus 2, which is 2, 4 minus 3 is 1, and then that equals 24. So anything to the factorial is basically right, yeah. So 120, and you can get to really big numbers using factorials, but that's beside the fact. So like right here, you see there's a table. They get really big as you go on, right? And then 7 to the factorial is 5040. Okay, so how many ways are there to arrange 5 people in a row of 5 seats? Right, so the correct answer is 120. Nice job. So it's basically 5 to the factorial because let's say there are these 5 seats right here. The first seat, there are a total of 5 people that can sit in this seat. So that's 5 multiplied by, so since you've already sat someone right here, there's only 4 that can sit here now. And then since you placed already 2 people, there's 3, etc. to until there is only 1 place for the last person to sit. And then that's 5 factorial, which we've already said is 120. So nice job, guys. Okay. Let's try example number 2. How many 3-digit positive integers are there such that by using the digits 3, 4, so that you can create using the digits 3, 4, and 5, and you can't use any of the digits twice? Right, so the correct answer is 6. Nice job to the people who have gotten it. It's just so one you could list, since there's only 6, listing works, but so there's a 3-digit number, so there's 3 placements. So in that spot, you can either put 3, 4, or 5. So there's a total of 3 ways for someone to go in that spot. So then you'll have taken off someone, so that's that one. So in the next spot, there will only be 2 people who can sit here. And then the last spot, or digits you can be there, and the last spot there's 1. So it's equal to 3 times 2 times 1, which is 6. It's also 3 to the factorial. Okay. So this one's for math counts. Let's see if you guys can get this one. A girl has 5 shirts, 4 skirts, and 3 pair of shoes. How many different outfits can she create? So that's like assuming she takes one shirt, 1 skirt, and 1 pair of shoes.
So 120 plus 94.
So 5 shirts, 4 skirts, and 3 pair of shoes. Right, so nice job, guys. The answer is 60. So like 5 total number of shirts, 4 total number of skirts, and then 3 pairs of shoes. So multiply those together, total of 60 outfits. So if you know how to do it, it's not too hard. Okay. Okay, let's go back to this problem right here. And then what if I ask the question, how many 3-digit positive integers are there by using the digits 3, 4, 5, and 6? And then we're just going to ignore this last sentence. So instead of saying no digits can be used twice, I'm just going to say you can use the digits twice or 3 times, or any number of times you wanted to use them. So how many 3-digit positive integers are there such that you can use the digits more than once. That's a very large number. If we thought about it, initially, our answer without using it twice was 6. It shouldn't be. I'll let you guys think about it. Right, so the correct answer is 27. Nice job to whoever got it. If you think about it, so last time when I was doing the thing, I said there were 3 here, and then since we used this one, there were 2 here, and then since we used 2 already, there were 1 here, right? But in this case, if I have the 3, the first digit, the hundredths digit can be any of these 3 digits, so there's 3 possibilities. The tens digit can also be any of these 3 digits. Since now we're allowing using it twice, so there's another 3. And then the last digit can be also any of these 3 digits. So there's a total of 3 times 3 times 3. So it's 27. Okay. And I think we're going to end class there. Thanks for coming. We'll have class again next week, same time. And I will post the notes on the board or on the class board. Okay, thanks. Have a good week, guys.